I'm creating this video to give you a quick introduction to the chi-square distribution. This is going to be a new distribution that we use. This distribution can be found on your calculator, on Google Sheets, and Excel. The purpose of this video is to introduce you to the main characteristics of this distribution. Let's start by talking about when we use the chi-square distribution. We're going to be using the chi-square distribution when conducting hypothesis tests involving qualitative variables, also known as categorical variables. And so again, this is really important. If you're conducting a hypothesis test and you notice you are working with qualitative variables, then you know that you need to use the chi-square distribution. Recall that when we were looking at numerical variables, we were using the normal distribution, the t-distribution. Now that we're going to do hypothesis testing for qualitative variables, we're going to be using the chi-square distribution. In this type of hypothesis testing, we ask ourselves, is the count on each category different than the count we were expecting to see? And we do expect to see a difference. But the main question we're asking ourselves here, is there a statistical difference? Is there a significant difference? This lesson is going to help you get ready to conduct those type of hypothesis testing. That is why we're looking at the chi-square distribution. Okay? Now, we're going to look at the main characteristics of the chi-square distribution. When we refer to the chi-square distribution, we use the notation chi-square. This is a Greek letter that looks like an X, like a capital X, and then we square that Greek letter. When you see this notation, you read this as chi-square. And so let's go ahead and make a note to ourselves. This is read as chi-square. This distribution is going to be a non-symmetrical right-skewed distribution. The mean of this distribution are going to be the degrees of freedom, and the standard deviation of the distribution is going to be the square root of 2 times the degrees of freedom. The chi-square distribution is used for different tests. Each test has a different way of calculating the degrees of freedom. So once you have the degrees of freedom is going to be the mean of the distribution. Then you can go ahead and take the square root of 2 times the degrees of freedom, and that will be the standard deviation. So how is the chi-square distribution created? The chi-square distribution is composed of the sum of square standard normal distributions. So imagine that you have a standard normal distribution for one of the variables. Let's imagine that we're talking about the Z1 distribution. Okay, again, the standard normal distribution for one of those k random variables. If you go ahead and take the square of all those z-scores under this distribution, remember the standard normal distribution is composed of z-scores. So if you take the square of each of those z-scores, I'm just going to write z square. What's going to happen? What type of distribution are you going to get? You're going to get a distribution that is right-skewed. I mean, think about it. So when we take the square of those z-scores, most of them are going to be a value close to 0. Okay. Again, think about it. The z-score here at the center of the standard normal distribution is 0. If you take the square of 0, you just get 0. Okay. Now you're going to have some z-scores, and most of them, again, are going to be close to 0. Okay. When you take the square of values that are close to 0, you're going to get something close to 0. Okay. Now, we do have some values, some z-scores that are more than 2 standard deviations away from the mean. So when you take those z-scores, let's say the z-score equal to 5, and you square that z-score, you're going to get 25. Okay. What about the z-score equal to -6? Well, you're going to get -6 to the power of 2. That's 36. That is why the distribution composed of the square z-scores is going to be right-skewed. I mean, you don't have that many z-scores that are larger than 2 or smaller than -2, but you do have some. And so when you square those z-scores, you're going to get large values. Again, that is why the distribution here on the right is right-skewed. Okay. So here we're saying the chi-square distribution is equal to the sum of the square standard normal distributions for these variables. Okay. So that is why we see z1 squared plus z2 squared plus ... plus zk squared. Okay. Again, here we're talking about a total of k standard normal distributions. We're squaring each of those standard normal distributions and we're adding them. Now, this is not something that you need to memorize. This is me explaining why we have a right-skewed distribution for the chi-square distribution. Now, you're going to get a different chi-square distribution depending on the degrees of freedom. And so that is what you see here on the graph below. Notice here you have some examples. You have the distribution for degrees of freedom equal to 1, equal to 2, 3, 4, 6, 9. Notice as k increases, we start to see that the curve approaches a normal distribution. And so that is the case. As the degrees of freedom approaches infinity, or gets larger and larger, or gets bigger and bigger, the chi-square distribution approaches a normal distribution. And so the rule of thumb is that if your degrees of freedom is greater than 90, then we say that the chi-square distribution approaches the normal distribution. Now, the last comment that I'm going to make here is that the mean, mu, is located to the right of the peak of your distribution. And we're expecting to see that, right? When we were calculating the mean for the first time, we saw that when we have outliers, or when we have a distribution that is right skewed, we see that the mean gets pulled up, the mean increases because of those outliers. Okay? So we are expecting to see the mean to the right of the peak.